color image encryption using Narain chaotic map, written by Hamza Abdul Karim and Hikmat N. Abdullah, published in International Journal of Wireless and Mobile Computing (IJWMC) on January 2019 on volume 17, page 212 until 218.
Traditional encryption methods like RSA, AES, and DES work well for encrypting text but don't fit well for encrypting image for two main reasons. First, images are much larger in size compared to the text, so it takes longer for traditional encryption system to process them. Secondly, the traditional encryption system requires the decrypted and original text sizes to be the same, which isn't necessary for image. Chaos signals have special qualities that make them great for encrypting images and making encryption systems stronger against attack. Because of this, mixing chaos theory with cryptography is a big deal in keeping information secure. Several image encryption schemes has been created before chaotic Narain map. For instance, new color image encryption scheme introduced by Xiang Jun. The encryption algorithm has been divided into four processes. First, image division shuffling process, where the color plane image is divided into four sub-images and the position of pixels in the entire image are shuffled. Then, in the key stream generation process, key streams are generated using the CML, which is the coupled map lattice. And image permutation is carried out using the key stream generated in the process step during image permutation process. Last but not least, during image diffusion process, the key for the image diffusion process is generated using a fractional order chain chaotic system. Next is the novel method for image encryption using chaotic map is proposed by Amir. The encryption algorithm has been divided into three phases, which is the secret key generation phase, where two secret keys are generated, which is CK and AK. Next, diffusion phase, where combination of two high-level chaotic maps, namely logistic CNS and power logistic, is used to construct a chaotic matrix. Lastly, indexes produced from two newly discovered high-level chaotic maps are utilized to modify pixel position, thus achieving permutation during the permutation phase. And last but not least, a color image encryption using 3D chaotic map with AES key dependent S-box is presented by Ashwak. The encryption algorithm consists of two stages of diffusion and two stages of scrambling. First, diffusion is where exclusive XOR is applied to diffuse the image in the first stage. Then a 3D logistic map is utilized in the second stage to generate secret key, which are then used to scramble the image. In the third stage, a 3D Chebyshev map is employed to generate secret key for the purpose of diffusing the image. During the scrambling, coordinate value using 2D Arnold-Cat map, it's involved using a 2D Arnold-Cat map to scramble the coordinate values of the AES S-box, thereby enhancing its secrecy. The previous method for image encryption were quite basic. They didn't take advantage of newer chaotic map to create encryption keys, nor did they use different chaotic maps for various encryption stages. So, this work aims to address this shortcoming by integrating recent advancements, particularly the Narain chaotic map, to ensure more secure image transmission.
And the objectives for this research paper is: first, analyze the advantage and disadvantage of the current image encryption methods. Second, to study the ways that chaos theory can improve picture encryption by making use of characteristics like non-predicity and pseudo-randomness. Third, analyze past image encryption methods, identifying their shortcomings and limitations. Fourth, using the Narain chaotic map, develop a new picture encryption technique that prioritizes key creation and increase security. And the last one is indicate in detail how the new method advances secure picture transmission by providing innovative solution to current issue.
Explanation and demonstration. Encryption process aims to generate encryption key from a Narain map for image encryption. Producing key image encryption depending on Narain chaotic sequence will increase the key space since it will depend on the initial value and parameters at map. Pixel value of shuffled image are modified sequentially by the encryption key image. As you can see, where A and B are the bifurcation parameter of the system as a result of a set of numerical models and associated simulation via MATLAB. A equal to 1.52, B equal to 0.05, X equal to 0.3, Y 0.2, and Z 0.1. The behavior counted system is very useful in security systems to disorganize the communication data in order to increase security requirements. The input number used in the test are the key generated from the dynamic system in time domain, and the output is a number between 0 and 1. The following result of a asymptotic cross-read key for different system variables are obtained. Kx equal to 0.9864, ky equal to 0.9866, kz equal to 0.9856. According to the result, since all the system variables produce number very close to one, that it is a chaotic system. The randomness tests are used to prove the randomness of chaotic random bit sequence RBS. We can see that the p-value of all the generated binary sequences are much higher than 0.01.
Suppose we have a color image represented by three components, which are red, green, and blue. The proposed algorithm for image encryption using Narin chaotic map involves the following steps. Step 1. Arrange the pixel of the color image components red, green, and blue from top to bottom and then left to right respectively to obtain three one-dimensional vectors, which are red component vectors, green component vectors, and blue component vectors. Step 2. We shall convert the three one-dimensional vectors PR, PG, and PB to binary vectors PR, PG, and BB, as shown in the table below. Step 3. Apply the Narin chaotic map to the binary vectors PR, PG, and BB to generate encrypted binary sequences. Last but not least, step 4. Convert the encrypted binary sequences back to the pixel value of the color image components red, green, and blue.
Here in this slide are the simulation results. As you can see, on the left side is the plain image or original image, while on the right side is the same image but it has been encrypted. Here is the results of correlation coefficients of two adjacent pixels, which are located on the left side of the slide. So as you can see, most of the correlation coefficients are near to 0. This indicates that the correlations among adjacent pixels in the original image can be effectively eliminated using the proposed method, thus enhancing resistance against statistical attacks. And next to it is the result of information entropy. As for this one, the proposed algorithm numbers are mostly near 8, which explains why random encrypted images are made. This is the results for number of pixel change rate, or known as NPCR, which is located on the top left of the slide. This NPCR will calculate the percentage of different pixel numbers between two images. As you can see, all of the proposed algorithm are 100%, which is the ideal performance. Meanwhile, next to it is the result of Unified Average Changing Intensity, or known as UACI. So this UACI will find the result of average intensity of differences between two images. In table 5, as you can see in Lawrence Green, and all of the proposed algorithm percentage shows that it is more than 32%. This means that the rate of influence regarding one pixel change is very large. And on the bottom of the slide shows the results of key sensitivity.
In figure 5c, the encrypted image has been decrypted with value A equals to 1.52 and B equals to 0.05, which result in be able to retrieve the original image. Meanwhile in D, a value of A equals to 1.52, lots of 0 and 1, and B equals to 0.05, the attacker won't be able to decrypt and retrieve the original image, even though there's only a bit of 0.01 something difference on a value, even if the B value is correct. This shows that a slight change of value will result in failure to retrieve the original image, which is also good because this ensures a degree of security for the proposed scheme against brute force attacks.
Okay, so in conclusion, we are able to get three main topics throughout the research paper. One of them being the limitations of traditional encryption for images. Just talks about how the research underscores the inadequacy of traditional encryption algorithms such as RSA, AES, and DES for image encryption due to the larger size of images compared to text. The processing time and the requirement for equivalent sizes of decrypted and original images are identified as significant challenges. And so, from that, we get the importance of chaos-based encryption, which chaos-based encryption methods leveraging properties like pseudo-randomness and non-periodicity are considered as crucial for enhancing the robustness of image encryption. Why is that? Because here we can propose a solution using the Noreen chaotic map, and so the research aims to address the identified limitations by proposing a novel image encryption based on the recent development of Noreen chaotic map. The goal is to integrate advanced chaotic maps for generating encryption keys and strategically use them at different encryption stages to improve the overall security of image transmission. And thus, the research seeks to contribute the development of secure image encryption by leveraging the unique properties of Noreen chaotic map. And that is all from me. Thank you.